This video is for those who are like me, having a hard time understanding how computers compute. We see humans manipulating symbols on a piece of paper as computing. But when people told me that computers use electricity as zeros and ones in the binary number system, and computing is performed by combining little switches to turn the wire on/off, I didn't understand. For many reasons. I didn't see those zeros and ones as numbers. And why computers use zeros and ones as numbers? Why not 2, 3, and 4? I didn't understand how can electricity be numbers. And I didn't see switching on/off as computing. Here's a joke about binary. See if you can get it. Been through all this, I'm going to explain how to overcome this to finally be able to see how computers compute. I split this video into several parts, so feel free to take breaks to avoid overusing your brain. We need to first talk about numbers. First, you need to realize that numbers represent physical quantities. We could assign different symbols to represent them. Because there could be an infinite number of physical quantities to represent, there is no way to keep making brand new symbols to represent them. That's why humans came up with a few basic symbols and rules to combine them to make new ones. There are mainly two schools, non-positional such as Roman number system versus positional like Arabic system. They are different in the rules around how to combine existing symbols to make new ones. You can probably see that Roman numbers seem messier than our Arabic ones, not just because we are familiar with one but not the other. There are more profound reasons. Most of us will have little problem with small quantities, but large quantities seem overwhelming. I think the reason is because of our brain limitation. Most of us can hold 7 items in our working memory, which is some place in our brain that process the raw data and form conclusions. But we seem to be okay with a small number of bigger objects. So positional number system makes use of such trick by successively bundling up a few items into bigger and bigger one. For example, to make sense of this quantity, we start by organizing one by one till our comfort limit. Say, I can only recognize 3 items comfortably. Reaching that limit, I can bundle them up into a bigger bundle and place aside. Then I keep organizing 1, 2, 3, bundle up and move aside. Keep going till we have 3 bundles in the middle bucket. I can certainly recognize 3 bigger ones, so time to bundle up again and move aside. Keep going till the full quantity is organized into different bundles. You can certainly use a bigger bundle size if you are comfortable, say a size of 10 in our Arabic number case. And in the computer case, the bundle size is 2. All you need to remember is, never leave more than 2 items in the bucket. So reaching 2 items, time to bundle up and move aside. Now how to record them? It depends on what are the purposes for those records. If you need to communicate those quantities, or to get human computers to compute on them, an easy way would be to write them down on paper. We simply record the quantity of different bundles. In our Arabic case, there could be 9 different quantities. For a bundle size of 3, there could be 1 or 2 items. In the binary case, max 1 item. So we invent symbols to represent those basic quantities. Using them to record those different bundles, here comes the number. But it's inconvenient to draw boxes reminding us what bundles we're talking about. That's why it's important to invent a separate symbol for 0, meaning an empty bucket, so that we won't mess up those buckets. Many of us see 14 as number, but not others. Only because we've been brainwashed with Arabic numbers, but not others. One way to see all this as legitimate numbers is to see them as nothing but code, waiting for us to decode. To do that, we have to know what bundle size each symbol is sitting on. These are called place values typically. For example, since every 3 items are bundled together, the unit will progress at a rate of 3, and in the Arabic case, a rate of 10. In terms of binary, a rate of 2. To decode what they represent, we need to combine the meanings of those codes with the units. The 1-4 here means a 10 and 4-1. This 1-1-2 is saying a 9, a 3, and 2-1. The binary case, an 8, a 4, and 2. They correspond to different number bases. So I hope now you see those different codes as legit numbers. The next question is how to do computing. Then we need to understand what is computing. Addition is about merging two physical quantities. The nice thing about positional number system is, regardless of what we're adding, in each bucket there could be only a few possibilities. All we need is an addition table listing those interactions. In base 10, 10 possibilities, from 0 to 9. In most cases, you just append those quantities together. But when reaching the bundle size, time to bundle up and move aside. Using abstract symbols, here comes the addition table. It's a lookup table to add two numbers. A carry out means to move into the next bucket. So for the positions with a carry in, we just add twice. The base 2 case is easy because there are only 4 scenarios, 2 zeros, a 0 and 1, or 2 ones. But remember in base 2, every 2 items will be bundled together. That's why the addition table will say 1 plus 1 equals to 1, 0. The binary form for 2. Any addition in base 2 can be done by following this table to add digits by digits. In base 2, they are called bits rather than digits. In base 3, this table is 3 by 3. Again, we can do computing by following the table. I will leave it to you to verify that both codes represent 21. I hope by now you view those strings of zeros and ones on paper as numbers, and symbol manipulation according to addition table as computing. Now let's think about what can be used here to represent numbers. Almost anything, because it's what they represent matters, not what they are. So you would agree these on-off switches would also work. Their on-off status can be used as the two basic quantities. The addition table will take a new look. To do computing, you just switch according to the table. Plugged into the power lines, they are effectively controlling the electricity beneath. But computing is not automatic if we still need human to do the switching. We need devices that can auto-switch. The secret behind the full automation of modern computers is this piece, an electricity-controlled switch called transistor. It can be triggered by high or low voltages to turn a wire on off. To see how transistors can carry out computing, remember that we only need to know how to add 2 bits. In computers, an adder is used to take 2 electricity inputs and spit out outputs. We're going to see how to combine several transistors to build this adder. But first, we need to know exactly how to represent numbers using electricity. This requires us to understand a bit more about transistor. It's made of silicon. Its conductivity sits between a conductor and an insulator. If you inject phosphorus, you are making the material called N-type conductor. If you inject another type of material, say boron, you are making the P-type conductor. If you start with the silicon wafer, inject boron in the middle and phosphorus on the side, you are making the NPN sandwich structure. And the middle layer will form an insulator due to the interactions between the 2 types. Of course, you can inject phosphorus in the middle and boron on the side, making the PNP sandwich. Its middle layer is also an insulator. The sandwich structure allows you to control its conductivity. If you place a sandwich, say at NPN to a power line, then you stick a wire to the middle called base, and then apply high voltage, say voltage higher than 5 volts, whether 5, 6, 7 volts. The middle layer becomes conducting, and now electricity is able to flow. But if you apply a low voltage, say voltage lower than 5 volts, whether it's 4, 3, or 2 volts, The middle layer would become an insulator, blocking electricity flow. It's an electricity-controlled switch. Now let's think about how to represent numbers using electricity. When we use humans as computers, we seem to be able to train them to remember any basic symbols we like. Seems that we can use whatever number base we like. But this transistor can only recognize two things: a low voltage unable to turn it on, and a high voltage able to turn it on. I'm using a gray color to represent low voltage, and yellow for high voltage. They can be used to represent two basic quantities, a 0 and 1. That's why computers use binary number system, because transistors can only understand two numbers. And now, the addition table is written in the language of high or low voltages. And the adders we're about to build will take high-low input voltages as numbers. The output will also be high or low voltages. This is how the sandwich could look like from the outside. The sandwich is inside this black box. 3 legs sticking out are for connections. 2 legs allow you to connect it to power supply. The middle leg allows us to control. If you apply the appropriate voltage, it will become a conductor. This little piece is at the heart of modern electronics. It won these 3 men the 1956 Nobel Prize in Physics. There are many new types of transistors with improved technologies. For simplicity, we will use the sandwich structure for illustration purposes. In the future, we will talk about its limitations and discuss more popular transistors used nowadays.